In this video, we're going to talk a lot more about capacitance and really try to understand what does this quantity mean at a physical level. Now, the definition of capacitance is fairly straightforward. In a capacitor, or any object that has capacitance, you have two plates or two objects that have charge on them. One of them is positive, one of them is negative. You take the charge on that positive object and you divide that by the voltage difference between the two objects. That's what capacitance is. But what does that mean physically? That's the real question we're going to try to understand. And people usually get this wrong. It's fairly natural to think that capacitance is the capacity of a capacitor. That is to say, the capacitance is the amount of charge that you can hold in a capacitor, or maybe the amount of potential energy that you can hold in a capacitor. But that's not what it is at all. It's in fact a very different quantity. So be careful not to think, because the name sounds like it should be the amount of charge or potential energy it can hold, that's somehow what capacitance is. Instead, capacitance talks about how it gets harder to put more and more charge on. Because as you add each charge, it takes more and more energy. And capacitance measures how quickly it goes up. If you have a very large capacitance, the amount of energy to put on each new charge stays close to the same. It rises very little. If you have a very low capacitance, each new charge takes considerably more energy than the last one did. We're going to use an analogy with fluids to try to understand exactly what capacitance is. So I'll make the following analogy between a capacitor and what's called a pair of standpipes. Now, here just imagine you have two buckets, essentially, on the left of water. Both of these buckets have water flowing in or water flowing out. In here, that's analogous to the plates. The plates are like buckets. The pipes are like wires. And instead of using electrons in the electric case, we're going to be talking about water flowing in the fluid case. Now, if you flow electrons into this plate, it'll get to have a very low voltage. If you flow electrons out, it'll have a high voltage. Similarly, there's going to develop a voltage difference between the two plates. Similarly, if you flow water into one side, the base will have a very high pressure, and down here the base will have a very low pressure if we continue to drain water out this side, because the height of these columns changes. And therefore you get a pressure difference that develops across these two. In both, the stuff that flows, electrons or water, does not physically cross from one side to the other, but it flows through either the wires or the pipes as if it did. In this analogy, a high capacitance pipe would be a very broad pipe. What that means is that as if water flows in, the height changes more slowly. If I, for example, put a gallon on the narrow pipe and pull the gallon out of the narrow pipe, the height would change a lot because they're fairly thin. However, if I had a very broad pipe on each side, as I put a gallon into this side, it would rise relatively slowly, and if I pulled a gallon out the other side, it would drop fairly slowly. Which means that the pressure difference would be less for the wide one than the large one for having flowed the same amount of stuff through those pipes. And so in this analogy, the capacitance would be like the area of the sandpipe. It's not how much it can hold, that would be equivalent to like how tall these pipes are. And it's not a question of how much stuff is in there, nor the amount of pressure that's at the bottom, which would be like the voltage difference.